The second macronutrient that we want to talk about is going to be carbohydrates. So we're going to talk a little bit about what makes the structure unique, how you're going to name it, how you're going to identify it, and then we're going to talk about how those carbohydrates are broken down to give you the energy that you need. Carbohydrates are important for your diet because they're going to help provide you with quick energy. They're simple to break down, some of them simpler than others. And so, again, that's going to give you those quick energies. So, carbs include your sugars and also your starches. Now, one of the most common that we talk about is glucose. Glucose is your blood sugar. Now, if it comes from corn, they'll add the word dextrose in instead. So, same structure, just different originations. Sometimes they'll call this food for thought because this is what's going to supply energy to your brain. It helps keep the body at a constant temperature. It helps you allow you to flex muscles, keeps your digestive and respiratory system running. So you have to have some carbs in your diet. If you don't, your body isn't going to function quite the way that it should. Now, down on the bottom, we have these little monosaccharides. We have down here glucose, which is what we were talking about earlier on this slide. And then we have fructose. Now, what do you notice? Glucose, dextrose, fructose. Do they all sound kind of similar? We'll look at that a little bit closer. Now, this slide has a ton of information about carbohydrates on it. The first thing we want to do is we want to look to see what makes up a carbohydrate. That's carbon. And what does it mean by hydrate? Usually hydrate is like water. Water's made of hydrogen and oxygen. So a carbohydrate only has these three elements: carbon, hydrogen, and water. I'm sorry, and oxygen. Wow, almost said water there. Now, what you'll find is that generally there's this 2-to-1 ratio of hydrogen to oxygen that really highlights that idea of a hydrate or a water. So let me give you an example. For example, up here we have glucose. Now, glucose, you're going to find out, has 6 carbons. It has 12 hydrogen, and it has 6 oxygens. Notice that it has twice as many hydrogens as it does oxygens. Now, some people might want to try to write it this way. They're going to write it as water and say, oh, there's 6 waters. This is an incorrect way to write it. You don't want to write it quite that way, but it does really emphasize this idea that we have some ratio or some relation between the hydrogen and the oxygen. Now, the way that we're going to classify these different carbohydrates is based on the number of connected sugar molecules, or the different saccharides that are put together. A monosaccharide is just one sugar. So at the very top, we have some examples of monosaccharides. So here's glucose. And then we have fructose. And fructose, we know that as fruit sugar. It's in a lot of honey has fructose, and also a lot of your fruits have fructose. That's why it's called a fruit sugar sometimes. Now notice they're just one little molecule. Now what we can do is we can combine these different molecules together in what we call a disaccharide. There we go. There's our disaccharide down at the very bottom. So we have some examples. This first one is actually sucrose. And to make sucrose, we took glucose and we added a fructose to it, and we bonded that together with this little oxygen down here. That's called a glycosidic linkage. Glycosidic linkage, there it is right there in your nose. Glycosidic linkage linked through an oxygen atom. On the right, this is lactose. And to make lactose, we take glucose, just like we did for sucrose, but this time we're going to add it to galactose, which is another monosaccharide. You can see these glycosidic linkages, this oxygen. We can have it to where the rings are on top. We can have it to where, like in the lactose, there's one that goes up and one that goes down. There's all these different little variations that we can do. So Mono is one sugar. Disaccharide means that we've taken two sugars and we've combined them together through a glycosidic linkage in oxygen. A polysaccharide has more than that. Now, the other thing to notice is that all of these saccharides end with the suffix ose, O-S-E, glucose, fructose, galactose, lactose. Now, that ose actually dates back to about in 1838. A French scientist committee was talking about the quality of sweetness. And this comes back from a Greek word, if you keep going back in time, for fermenting fruit juice or sweet wine. So let's learn more about these carbohydrates. The type of carbs that you eat can affect how fast or how slow they break down, or how fast or how slow you get that energy. So here we're going to look at the difference of high glycemic versus low glycemic index foods. A high glycemic index food is something that can be digested and absorbed quickly, meaning it's very, very quick to break those polysaccharides apart from one another. Now, because they can break apart so quickly, this is going to cause a rapid increase in your blood sugar. So if you're somebody that's dealing with diabetes, this is going to be an issue because then you have to have insulin to help kind of counteract that, and you're going to run into some problems. There's also an increased risk of obesity with these high glycemic index foods. These are going to be your refined sugars, also your flours, especially whenever you get into the enriched bleached white flour that's just so yummy and simple to use. Yeah, our body has a harder time. I don't want to say a harder time. Our body can break it down faster. So sometimes it's a little bit faster than what our body actually needs. A low glycemic index food is something that's going to be a little more complex. It's going to be something that's digested and absorbed slower, so our body has more time to adjust to that. These are going to be your whole grains, your whole fruits, the beans, the veggies, all of those good, yummy things. The healthier food that we sometimes will end up talking about. This is going to cause a more controlled change in your blood sugar. For our body to be able to use those carbohydrates, we actually have to break down the polysaccharide into monosaccharides. The monosaccharides can penetrate the intestinal wall and then enter our bloodstream. So then it can start affecting all sorts of good stuff. So our dye and our polysaccharides must be broken apart. The way that we do that is through a process called hydrolysis. This is a cleavage. Cleavage just means that we're going to break apart the glycosidic link. So remember, the glycosidic link was whenever we take the individual monosaccharides and we combine them, we bond them together with an oxygen. So here we have a little oxygen down at the bottom. That's our glycosidic linkage. But we're going to break that by adding water to go ahead and start breaking apart these different things. Now, it's not just by adding water. We also have to use, you'll learn about it on the next slide, so hang on. All right, so here's another slide, again, with a whole bunch of information. Now, we were just talking about for our body to be able to use a carbohydrate, we have to break apart the polysaccharides into monosaccharides. Well, one way to be able to do that, to help with that, is through the use of enzymes. Enzymes are a biological catalyst, meaning that we can make reactions occur more rapidly. That's good, it's faster. Or it can be done under milder conditions. That's really, really important for our food because remember we talked about we don't have an actual combustion reaction because we can't have those high temperatures. So we need something that has milder conditions. That's why we have enzymes. So let's look to see what this enzyme looks like. So here we're going to go down to the bottom right. And an enzyme is this really, really large, well-defined sites type thing. Now, if you notice, this enzyme right here has two little openings in it. And along comes a polysaccharide. This is a disaccharide. Now, this has to be a specific disaccharide because it only fits in one way. And if we don't have exactly the right disaccharide, it's not going to fit into those enzyme sites, those active sites. If it'll fit into those active sites, then hydrolysis will occur. So we'll break apart the disaccharide into two monosaccharides, and then our body can use those. But it has to fit in just right. So again, we have very, very specific carbohydrates that this is going to work on. And the name of the enzyme is actually based on the name of the carb that it works on. So here we actually have that picture. This is for sucrase. Sucrase works on sucrose. So you'll notice the enzymes end with ACE. Sorry, that's kind of chumpy there. And the carb ended with ose. And so you'll see how those two are going to relate to one another. Now, another enzyme that we often talk about is lactase. Okay, what does lactase work on? Lactase, oh, you got it. It works on lactose. Where have we heard about that before? Are you lactose intolerant? What does that mean? Where is lactose? What food is that in? Well, lactose a lot of times in our dairy products. And some of us are missing these enzymes to be able to break down that lactose. We're missing our lactase. Now the lactase will hydrolyze lactose into glucose and galactose. So it tries to take that disaccharide and break it down just a little bit. So let's see here. So lactase is used to help digest dairy. The more milk that you drink, the more lactase that you need. It's going to, again, break the lactose down. Now, it's estimated that babies have about 40% of their calories from their mother's milk lactose. As we grow, we actually lose the ability to produce lactase. And so as we grow, a lot of us end up having issues being able to digest dairy correctly. So we have to watch the amount of dairy. This one actually, your ethnicity can play a part in it. It's estimated about 3% of people from Northern European descent, up to about 80% of Asian descent are lactose intolerant. So what happens if you are lactose intolerant? What happens if you don't have enough lactase in your body? Well, if you don't have enough lactase, that means the lactose can't be broken down. It's not hydrolyzed. It can't be absorbed. It passes into your intestines, and there it'll ferment into what's called lactic acid. It'll also produce carbon dioxide and some hydrogen, and it ends up causing gastric distress. So if you notice after you ingest dairy, so if you drink milk or maybe some cheeses bother you, if your stomach has some distress, this could possibly be a reason why. We are really complex beings. If you think about it, it's amazing how little things can have a huge influence. Here we're going to look at the difference between starch and cellulose. They're both made up of glucose monosaccharides. But the difference is how that glycosidic linkage occurs. Are all of the glucoses on what's called the same plane, or are they on different planes? Are they kind of flat, or do they kind of go up at an angle? So at the top we have starch. So here's our starch. There's starch. Everything's in the same plane. We call that an alpha link. Alpha. There's a little alpha. Now it turns out that starch we can digest and we can absorb. We can use starch to be able to get energy from. But cellulose is different. So cellulose is sometimes called fiber or roughage. It's this bottom one, the same basic structure, but we have a beta link instead of an alpha. So if you notice, they're not side by side, they go up. Now, this is going to cause a problem because our bodies can't break this apart. Now, this roughage or this fiber is going to pass through the body unchanged and unabsorbed. There's more cellulose on the earth than any other single organic compound. It doesn't occur in animals. This can range from several hundred to 1,000 consecutive beta-glucose rings. So humans just can't deal with this. We don't have enough enzymes or the right type of enzymes to recognize this beta link. We can recognize the alpha link though. So on this one, we have an enzyme called amylase. Amylase is going to hydrolyze starch into smaller segments, such as disaccharides called maltose and a bunch of other cool things. Now, the idea of the alpha and the beta linkages, you can dive really deep into that. I just wanted to introduce it to you, but I wanted to go ahead and show you this picture because it looked kind of cool. You can look at what's called an open chain glucose. We can talk about aldehydes and ketones. There's all sorts of different things to add to that. Here we're trying to show what happens to that link if the OH group, here's a little OH group, if it's on top or if it's on bottom and how it's going to link to the next one. Sometimes they compare it to a fox where the tail's above the nose or below the nose. Just know the basics. If you want more information, go read your book on that part.